Welcome back to ECE 501B. Homework number 4, I think, is available for you, and that's due on the 19th, which I think is a Friday. So it's not due on a normal class meeting day, just changing it up or mixing it up on you. And there's also some additional material on finding or computing eigenvalues and eigenvectors on the D2L website that you're on your own to examine. And that's what I'm calling lecture 4.2E for extra. So that's following last time's material. Today what I want to do is continue with our examples of these 1D invariant subspaces, and we'll look at example number 2 of that for computing eigenvalues and eigenvectors, and then we will start looking at some of the key results in chapter 5. The first one being linearly independent eigenvectors, and we know the power of having linearly independent vectors. If we now have distinct eigenvalues, and we'll make clear what that means, but if we have a distinct set or a set of distinct eigenvalues, each one of those distinct eigenvalues will have a linearly independent eigenvector associated with it. That's Theorem 510. Corollary to that is Corollary 13, which says that the number of distinct eigenvalues of this operator is less than or equal to the dimension of V. It can't be bigger than V is basically what that's saying. And the number of distinct, you might just have one eigenvalue for a 10 by 10 matrix or a 10 by 10 operator. What could that look like, or what would that look like? An eigenvalue, one eigenvalue for a matrix that's 10 by 10. We did it the last time we met. It was A times I, right? It's the identity operator. The eigenvalue is A for that particular operator. So there are cases where you may not have 10 eigenvalues for a given 10-dimensional operator. You may just have one that's distinct. Then we will start looking at how we can build more complicated functions of operators, and in particular this operator that sees quite a bit of use, and that's the matrix exponential. What does it look like to take the exponential of a matrix? That's e to the a. And then we'll look at Theorem 521, which now guarantees that we have an eigenvalue. But there is a constraint on an operator having an eigenvalue. It needs to be a finite dimensional complex vector space in order for us to have the possibility of having an eigenvalue for a 1-by-1 operator, for example, or an operator on a 1-by-1 space, or in a 2-by-2 space. We could have a 2-by-2 operator over the field of reals, which we look, well, getting ahead of myself. So we'll look at that, where we might have a linear map from R2 that does not have any eigenvalue associated with it. But that's because we would be dealing with a finite dimensional real vector space, as our field is the field of real numbers. And then we'll get into upper triangular matrices. And upper triangular matrices are nice, and we're looking for nice operators or nice matrices. An even nicer matrix is a diagonal, a matrix that possesses a lot of zero elements. That's what we mean by nice. So let's get started. Here is our definition or relationship that governs the eigenvalues and eigenvectors that we defined last time, and those then are associated with invariant subspaces of linear operators T. When we say t is an element of script L of v, when we just have the one argument in the script L, that's saying our input space and output space are the same. So we're mapping from the input space back into itself. If we do have this equation, if it exists, if t omega is equal to lambda of omega, or maybe I should say tw is equal to lambda w, then lambda is an eigenvalue and w is our eigenvector. And you should be comfortable if somebody gives you tw equals lambda w, looking at that as the second equation on that same row, the quantity t minus lambda I times w. Or that's now telling you something unique about that vector w. It's in the null space of this operator t minus lambda I. So knowing null spaces or how to find null spaces is key to this eigenvector or invariant subspace concept. So let's now look at a 1D invariant subspace example that's different from what we talked about last time. Last time we talked about A times the identity operator. I think that was our example 1. Example 2, let's let it be the following. Suppose that now we have t operating on a 2 vector, w1, w2, and right now we're not saying where w1, w2 live. If they are real, then this is going to present us with the following. We now are saying that that linear map takes as its output vector, or maps w1, w2 into an output vector of minus w2 comma w1. And that we've talked about already, and that actually corresponds to a 90-degree counterclockwise rotation in the xy plane. If we are looking at the w's belonging to reals. So now we have a, let's say, in R2, or let's now look at that. So let's not specialize it just yet. We'll look at the specialization in a minute. But now let's look at what that says. The eigenvalue eigenvector equation says that we have tw is equal to lambda w, or that now says that what is tw? For w parameterized by w1, w2, we just showed what it was. It's now this. So let's now write that down as this expression. So now we have minus w2, w1. That's the left-hand side. And the right-hand side is just a scalar of the input vector. So that's now lambda w1, w2. Or that's lambda w1, lambda w2. We're trying to see, can we find values for w1 or lambda that satisfy this? w1, w2, and lambda, can we find solutions to this relationship? And now we have really two equations. We have one equation for each of the coordinates or elements in that equation. We have the first element. So if we look at the first coordinate, that now says that we have minus w2 is equal to lambda w1. Or if we want to get rid of the minus sign in front of the w2, w2 is now minus lambda w1. That's from the first coordinate. The second coordinate now gives us w1 is equal to lambda w2. But we now have an equation for W2 in terms of W1. Let's put that in. We now can say that that's lambda times minus lambda W2, or this is now minus lambda squared W2. Ah. Is that better? So W2 we said is minus lambda W1. We're replacing that expression in for W2, and we end up with now W1 equaling minus lambda squared W1. Or, if we want that to be true for all W1, then what does that tell us? So now if this is if we're dealing, so now I'm saying here's our coefficient on the left. We have 1 times W1. That's equal to minus lambda squared W1. For all W1, that says lambda squared is minus 1. Right? So now we know, or this coupled set of relationships tells us that we now have lambda squared is equal to minus 1. So now let's look at what that means, or what that implies. Suppose that, so up until this point we haven't defined our field. Let's look at particular fields and see what that does to the solution of this, or does it allow solutions. So now if, let's say that now f is equal to the reals, what can we say? What real numbers allow us to square them and equal minus 1? That's the whole point of why we developed complex numbers, is for this case, right? Lambda squared plus 1 equals 0. So now this says that no real number solution exists for lambda squared equal to minus 1. So that says then if we're working on the field of reals, then there's no invariant subspace or no invariant directions exist. And that makes sense, because what does this map do over the field of reals? It does this 90 degrees rotation counterclockwise. So rotations of 90 degrees, or let me say rotations in R2 by 90 degrees, that does not preserve any directions. So if we were trying to find an invariant direction, we want to now see, is there a direction which when we operate on it by this t, we get back on that same direction or end up in that same direction. And that's not possible for this linear map or this linear operator when the lambdas and the w's are constrained to be real. So let's look at the other case. Let's let the field be complex. We have the same derivation or development. Now we're looking for lambda squared equal minus 1, and this is how we started to define complex numbers. So now we want this to be plus or minus the square root of minus 1, and in this electrical engineering case, that's now plus and minus j, or plus and minus I if you're looking from a physics or math lenses on this. Or now if we wanted to plot these lambdas in the complex plane, we have one up here at j, and we have another one at minus j. So here is the real, and here is the imaginary axis of this complex plane. And the point I'm trying to make is that that x above the real axis and that x below the real axis are not on top of each other. They're distinct. So plus j is distinct from minus j. So if we have anything that has conjugate relationships, those two conjugates are not the same point or value. They're distinct. So now let's see if we can find eigenvectors associated with these eigenvalues. We did find a lambda, and we know the relationships on the w's. Let's see if we can find those so that we can actually have invariant directions over the field of complex for this linear map T. Suppose in the first case we look at lambda equal to plus j. In this case, we have minus w2, w1. This was what? This was the tw, wasn't it? And that needs to equal lambda w, and lambda was plus j for this case, and w is w1, w2. Or this is now j, w1, j, w2. Now, what's happening here? Let's look at the two coordinates. So one of the coordinates says that minus w2 needs to equal j omega 1. What's the other one say? Well, that says that w1 needs to be j omega sub 2, or w2. And those are actually the same. So we have redundancy when we look at the two different coordinates. And that's good because that's really what's giving us this non-trivial null space solution. This is the same relationship that I've now shown in both the first coordinate and the second coordinate. So it really doesn't matter which one we work with. They are both going to give us the same relationship between w1 and w2. So let's look at the first one and say that that's now minus w2 is equal to j w1. Or w2 is now equal to minus j w1. And now we have a relationship between w1 and w2. Now we can say that the eigenvector let's say associated with lambda equal to plus j is actually, let me say the vector is w plus for the positive eigenvalue, is now w1 is the first coordinate and the second coordinate is w2, but that can be written as a function of w1. It's now minus j omega 1, and that's with w1 coming to us from a complex field. So you give me a w1 and lambda equal to plus j, and I can satisfy this relationship. Tw is equal to lambda w. that now is a one-dimensional invariant direction. It's hard to imagine because now we have complex numbers in the two coordinates and we have a complex scalar. So it's not that easy to visualize, even if it is visualizable. Maybe it's not. I'm not sure that I see it, but the algebra works out. You take t that we had, minus w, which when operated on w1, w2 gives us minus w2, w1. That will equal lambda j times that vector. So you can do that and convince yourself that that indeed does satisfy that eigenvalue-eigenvector relationship. What about the other one? What about lambda equal to minus j? If we go through the same steps, there's TW, and that's now equal to minus JW. If we look at the first coordinate again, you can actually see that those two are giving you the same relationship again. Now if we say minus W2 is equal to minus JW1, now we can see that W2 is actually just JW1. And we could have guessed that relationship because we were dealing with real coefficients on our W's in the T definition. But not knowing that, we can derive those, and the eigenvector now associated with lambda equal to minus j is W minus, and that's equal to W1, and W2 is JW1, which is the conjugate of the previous of W plus, and this is now with W1 in the reals.
But if you multiply j by j over j, you're going to get the same. So if you multiply W2.
So now if you, what are you?
So if you multiply by j over j.
If you multiply W2 by j over j, which is 1, then
Never mind. Yeah, I missed that.
so you should get back the right relationship. And now what we're saying is either of these vectors are an invariant direction. So that if we now said T W minus, that's supposed to be minus lambda W minus. That's what we've derived. The other one says that T W plus is equal to plus J W plus. And you can go home and convince yourself that that is in fact, based on how we derived it, those are true. So now we know that TW is equal to lambda W for those two distinct eigenvalues. Yes?
Should it have been TW minus is minus J W minus?
Oh, where'd the lambda come from? So this is now supposed to be minus J. Is that what you were asking? Who knows where that lambda came from, but I was just going with it. So it should have been the lambda. It should be lambda of what we were using, and that lambda was minus J. Thank you. Other questions or corrections? So now let's get into some facts or relationships for eigenvalues and eigenvectors. And the first one that we will look at is Theorem 10 in Chapter 5, and this is dealing with linearly independent eigenvectors. That's the label on Theorem 510. And that says that the eigenvectors associated with distinct, eigenvalues of the linear operator those eigenvectors are linearly dependent. That's the theorem. The eigenvectors associated with distinct eigenvalues of the linear operator are Good thing I had the label there. I could check my work, huh? Linearly independent. Okay? So now the key here is distinct, and I want to make sure that we're all on the same page and make sure I'm awake when I'm doing this in terms of what we mean by distinct eigenvalues. So let's look at some examples. Suppose I give you -1, -2, -3, -1. That's one set of eigenvalues. Another set, let's say, is -1 plus j, -1 minus j, and -2. Or it even could have, let me say -1, just to make it a little bit more interesting. And now -1 plus 1. And I want to make sure that we all are seeing the same thing. The first set of eigenvalues, is that distinct or not distinct? Not distinct, because now if you simply put down your complex plane and start putting x's on these locations, if you double up on your x's, then you have non-distinct eigenvalues. Question?
Is this a set?
So this is a... Oh, is this a set or a list? So this is either one.
I thought a set didn't necessarily.
Okay, so it's a list. Thank you for correcting me. This is a list. This is a list because because a set, yes, you're right. If it was a set, so I was using the wrong descriptor, wasn't I, when I said here's a set, here's a set, here's a set. So here's a list, and here's a list. How's that? The first list is -1, -2, -3, and -1. So with a set, we really can't talk about that, can we? Because we can have overlap and the set will be the same. So these are lists. Lists. Okay? The first list. That looks a little bad, huh? Is the first list consisting of distinct or non-distinct eigenvalues? So we have a few that are unique, but we have one that's on top of the other, so this list is not distinct. These eigenvalues, this list of eigenvalues. So this is not distinct. But that means that there is the possibility that we would have at least 3 linearly independent eigenvectors associated with that list. We could have 4, but we know we have 3 because we have 3 distinct eigenvalues. But that list by itself is not distinct. So we know that we do not have 4. That's not distinct, okay? I shouldn't say any more. Because we can create a diagonal matrix that would have unique eigenvectors, or I'm sorry, linearly independent eigenvectors for that list. But it's not required. I'm making it more, this was supposed to be clearing things up. Okay, so the middle list, does it consist of distinct eigenvalues? Yes, they're all 3 points are not overlapping at all. What about the last list? If you were in a controls class, you might not like that last list because we have one eigenvalue that's in the right half plane. If this was associated with a analog system, it would be unstable. If it was associated with a discrete system, they're both on the unit circle, that's not good either. So those lists are not good for various reasons. All right, so now we know about distinct and not distinct lists. Let's see if we can prove this theorem. The eigenvectors associated with distinct eigenvalues of t are linearly independent. So let's look at a proof of that. And to prove this, first we're saying that we have this linear operator t, and let me simply establish notation and say that I now have m distinct eigenvalues, and their corresponding eigenvectors I'm going to label with v's. So this is now v1. That's an eigenvector. It's not an element. So here's the overloaded use of the subscript. But v1 is a vector. v sub 2 is associated with eigenvalue lambda sub 2. And so on up to v sub m. So those are the associated eigenvectors. And just to be clear, m, Michigan, is less than or equal to n, where n is the dimension of the vector space V. So I'm not necessarily saying that all of my, if I had n eigenvalues, I'm not requiring them all to be distinct. I just want to show that the ones that the eigenvectors associated with the distinct eigenvalues are linearly independent. I'm saying nothing about the eigenvectors associated with non-distinct eigenvalues. Is that clear? And what I want to do is actually prove by contradiction. And if that's the case, if I'm proving by contradiction, I'm now saying let's assume A and not B, and then try to follow down and find a contradiction somewhere. What's A? What's statement A? I have distinct eigenvalues, some list of distinct eigenvalues. M, a list that's M long, right? And B is then that the M eigenvectors associated with those are linearly independent. So now I'm assuming not B and the distinct eigenvalues and seeing if I can find a contradiction somewhere. What did I just say? So let's now assume that this list, V1, V2, of vectors is linearly dependent. And here I want to say linearly dependent. I'm assuming not B. So these are now, I'm assuming that those M vectors are linearly dependent. That means at least one of those vectors can be written as in the span of the others. So that means at least one eigenvector in the above list is in the span of the others. That's what we mean by a vector being linearly dependent. So now let me establish this in sort of an interesting way. Let L, that's an integer, be the smallest integer such that V sub L is contained in the span of V1, V2, up to V sub L minus 1. So I've ordered these eigenvectors in such a way that V sub L is the smallest integer such that it now can be described or written as contained in the span of the previous L minus 1 vectors. That's how I've ordered these vectors. Now that means that I can write V sub L like you were expecting. V sub L is now A1 V1 plus A2 V2 up to A sub L minus 1 V sub L minus 1. That's what the VL being in the span of V1 through V sub L minus 1 represents or means. Now let's apply the operator T to both sides of that equation. That equation is true by assumption. We assume that those vectors were linearly dependent, so we can find this equation. So now let's apply the operator T to both sides. Or I now have T V sub L is equal to, and let me slide the scalars to the left of the operator so that I now have A1T V1 plus A sub 2T V sub 2 on through to A L sub L minus 1 T V sub L minus 1. But we defined those V's to be eigenvectors. So now that operator on a vector can be what? In the same direction as that vector, just off by a scalar, which is the lambda. So TV1 can be rewritten as a scalar lambda 1 times V1. The same with all the other TVs. So now I can write this, TV sub L is now lambda L V sub L. That's the left-hand side. And the right-hand side is A1 lambda 1 V sub 1 plus A sub 2 lambda sub 2 V sub 2, etc. And we're able to do that. Here's the explanation. Since T V sub I is equal to lambda sub I V sub I, and we assume that these V sub i's were eigenvectors. And I like that equation, so I'm going to actually number it. Let me number that one 1. Are we okay with equation 1? Everybody follows that that is valid based on what we've assumed. All right, now let's recall how we defined V sub L. We defined V sub L to be this linear combination of the previous V sub L minus 1 vectors. V sub L is A1 V1 plus A sub 2 V2 plus A sub L minus 1 V sub L minus 1. I kind of like that lambda sub L V sub L on the left of that equality sign in 1. So let me get that to happen down here. Let me multiply lambda sub L on both sides on this equation. That's okay, isn't it? Didn't call it a set. Not yet. So let's now push this lambda sub L through all of these terms. Multiply it on both sides. So now I have lambda sub L V sub L equal A1 lambda sub L V1 plus A sub 2 lambda sub L V sub 2 plus A sub L minus 1 lambda sub L V sub L minus 1. Everybody okay with what I've done so far? Let me call that equation 2. And I simply found that by multiplying the top equation for V sub L by lambda sub L. Now let me combine 1 and 2. And by combine, I mean let me subtract 2 from 1. Equation 2 from equation 1. And now that gives me something nice on the left-hand side. 0. So let me combine 1 and 2. Equation 1 and equation 2. And that's going to give me equation 3, which now is 0 on the left, and what's on the right? It's kind of a mess. But I have A1 is the same. But now I have lambda 1 minus lambda sub L times V1. Plus, and now I just have that same structure for all of these other terms. A sub 2 lambda 2 minus lambda sub L V sub 2. And A sub L minus 1 lambda sub L minus 1 minus lambda L V sub L minus 1. Now, so what? That just looks like an ugly mess. But remember what we said about L, how we defined V sub L. So now we said because, or here let me just try to write it down, because that vector V sub L was the first by definition. That's how we labeled all of these vectors. V sub L was the first vector in our list of vectors that could be written in terms of the earlier vectors the list V1, V2, V sub L minus 1. What do we know about that list of vectors? They're linearly something. What are they? Dependent or independent? By the definition of V sub L, we assumed all of those were linearly independent. So now these must be linearly independent. But now, equation 3, we have a list of linearly independent vectors combined to give us as the 0 vector. And you know what happens when you combine linearly independent vectors with scalars and they give you the 0 vector. What does that tell you about the scalars? They all have to be 0. So let's write that down. Therefore, equation 3 implies all the coefficients are 0, or that is A1 lambda 1 minus lambda sub L is equal to 0. A sub 2 lambda sub 2 minus lambda sub L is equal to 0, etc. And now we have a product of terms equaling 0. That can be achieved two different ways. We really don't need to do it, but let's go ahead and do it. Let's say the first one is either, there's the one that we really have already assumed. We assumed that all of the lambdas were distinct, but if they weren't, so either there are non-distinct eigenvalues which is a contradiction, and so we could quit on that. Or here's the one that really is the one we need to worry about, because we already assumed that we had distinct eigenvalues. So really this second one is the one that is holding true, supposedly. So now 2 is that all the A sub j's are 0. Because we know we assumed that all of our lambdas were distinct up through lambda sub m. So we know those comparisons of lambda 1 with a different one, that's going to give us a non-zero value. So we can divide those out, and that says that A1 has to be 0, A2 has to be 0, etc. That's really case 2. So now all the A sub j's are 0. But V sub L was A1 V1 plus A sub 2 V sub 2 plus A sub L minus 1 V sub L minus 1. And what does that tell us about V sub L if all the A's are 0? V sub L is the 0 vector, and there's our contradiction. We assumed that it was an eigenvector, and those are non-zero. So this would imply V sub L is equal to 0, and that's a contradiction. Since we assumed it was an eigenvector to begin with. Therefore, we can conclude that V1, V2, up to V sub m must be linearly independent. So now if we have a distinct list of eigenvalues, then the associated eigenvectors for each of those eigenvalues in that list are linearly independent. That's pretty powerful. That allows us to actually find linearly independent eigenvectors, and we can do a lot with linearly independent vectors. Let's now look at a corollary. We'll just state this. This is now corollary 13, and this is dealing with the number of eigenvalues associated with a linear operator. Suppose T now is a linear operator on V. That operator can not have more than dimension of V distinct eigenvalues. So if we have a linear operator that's operating on a 10 vector, we can't have 12 distinct eigenvalues. We can't have 11. The most we could have is 10, and we aren't guaranteed of having 10. We could have one distinct eigenvalue, but we can have no more than 10. That's what this corollary is telling us. And I will let you look at the book for that proof, because we now want to go on to the next topic, which is creating more interesting operators. Let's now look at powers, polynomials, and functions of operators. Since an operator is a map, from a vector space to itself, it makes sense to use repeated application of that operator. So repeated applications of that operator are well defined. Meaning we could map or operate on TV with another T. So we have T times TV. We have T times TV times T times T times TV, etc. It makes sense because we're always going, the output is the same dimensionally as the input. So if T now is this linear operator on V, we will define T to the power M as T times T M times. That's what we mean by the mth power of an operator. Similarly, or consistent with how we've typically thought of anything to the 0th power, an operator to the 0th power we will define to be the identity map. So now, with this notation, now we can create polynomials of operators to give us more flexibility or more power. So with this, we can define polynomials of operators. such that if we had a polynomial p of z, which is now, let's say, a sub 0 plus a1z plus a sub 2 z squared up to, let's say, a sub m z to the m. And here I hope it's clear that this is z to the 0. That's 1. And this is z to the 1. Then that polynomial applied to the operator t can be built as a times the identity operator, or a sub 0, plus a sub 1 times t, a sub 2 t squared, and we've now defined what we mean by t squared, a sub m t to the m. And once we have polynomials, then we can start playing really, or building nice little functions. So now, once we have polynomials, we can even start talking about more complicated functions of operators. For example, if we are given f of z, and let's say f of z is some complicated function, then f of t, that complicated function of our operator t, we can define to be p of t, where p of z is the Taylor series expansion of f of z, where p of z is the Taylor series expansion of f of z. So if you have a complicated function f of z, then you can find its Taylor series expansion, p of z, and now we just set f of z equal to p of z. And if we have now f of t, we can find f of t by evaluating p of that operator t. Here's an example. Given, let's say t is a linear operator on a vector space V, and suppose that this complicated function f of z is actually this exponential, e to the z. Now we can look at the Taylor series of e to the z. And what's the Taylor series of e to the z? Remember, e to the z is nice to differentiate, isn't it? If we differentiate e to the z with respect to z, what happens? We get e to the z. So now we can differentiate this at will to give us e to the z is now the e to the z at z equal to 0. We're now a Taylor series, so we're expanding about z equals 0. E to the 0, 1, plus first partial with respect to z, evaluated at z equals 0, e to the z at 0 as 1 times z minus 0 raised to the first power. All of that to give us z, plus the second derivative of e of z. That's still going to give us 1 at z equals 0. But now we have 1 over 2 factorial, the quantity z minus 0 squared, and we just keep going. Now we can obtain a series expansion for this matrix exponential. Now we replace z's with t's, or powers of t. So the 1 becomes the identity matrix, or identity operator, plus t, plus 1 over 2 factorial t squared, plus 1 over 3 factorial t cubed, etc. And that matrix exponential is nice because we use it all the time. This operator is used heavily let's say in advanced topics. I'm not sure how advanced the last one is, or the first one. If we say that that's control, I don't know if you consider that very advanced, but anyway, that's control. You use that to try to find the state transition matrix, for example, which tells you how the system evolves with time, and you might see this then in quantum mechanics, the matrix exponential. So now we have a way of building that by this series expansion. It's probably not the best way to do it numerically, but we have a formula for it. And you can find more efficient ways or numerically stable ways to create e to the t. But let's just, for now, realize that we can build it up out of this series expansion. Question? So this is now a linear map, isn't it? So the question was, is this now a linear map? So now it's a, what is it? It's a linear combination of operators of t. And so now we just have to be able to create t cubed, t to the 4th, and apply that with the appropriate coefficient weighting. 1 over 3 factorial, for example. As I said, that's not numerically nice to do using these powers of t if those were matrices. But we're going to not worry about that here. We now have a way of creating complicated functions with operators, or linear maps that are operators. So is it a finite dimensional linear map? Is the question. What did we do with our input vector space? Did we change it? And how's the output vector space related to the input vector space? Same. So what's going on between those input and output might be a complicated mess, but that hasn't made it an infinite dimensional vector space. It may be an infinite sum of operators, but that hasn't changed our dimension of our vector space. Is that clear? So now let's get into another theorem which actually returns us to this greater than or equal to question from before, which I think that's a little bit, well, it has quite a few layers built into it, that greater than or equal to, and I was not, now let me state this for now. Every operator on a finite dimensional complex vector space FDCVS. You might go to CVS and pick one of these up, an FDCVS, finite dimensional complex vector space. Go ask for that at the counter and see what kind of a look you get. Of dimension greater than 0 has an eigenvalue. They may give you some really strong medicine if you go asking for an FDCVS. 911. I have a customer here that's asking for an FDCVS. I have no idea what he's talking about, or she. All right, let's talk about the proof of this. So this is saying that every operator on a finite dimensional complex vector space has an eigenvalue. An eigenvalue exists. We know that's not true if it was in the real vector space. We looked at that at the beginning of this class. We had a a linear map, a linear operator operating on R2, a rotation, and that didn't have an eigenvalue. On a complex vector space, we do, as long as the dimension is 1 or more. Here's the proof. Given a complex vector space, V with dimension of V equal to n, and n is greater than 0. And our linear map T, our linear map is a linear operator. So now let's choose a vector, V, in that vector space, and let's say that that vector is not the 0 vector. Suppose we create the following list. V, TV, T squared V, up to T to the n V. What can you tell me about that list of vectors? This is a list of vectors. The key here is what's the length of that list of vectors? It's n plus 1, isn't it? And how big is the vector space? N. So what do you know about a list of n plus 1 vectors in an n-dimensional vector space? They have to be linearly dependent. So the list, V through T to the n V, must be linearly dependent since it has length n plus 1 and the dimension of V was n. Thus, if we write the following relationship on those n plus 1 vectors, 0 is equal to a sub 0 V plus a sub 1 TV plus a sub 2 T squared V plus all the way up to a sub n T to the n V. can we find coefficients, scalars, that will allow that to happen? And we know they're not going to all be 0, are they? Because this is a linear list, a linearly dependent list of vectors that we're summing up or combining. So we can find, so thus if we write that expression, we can find a set of complex, that's our field, coefficients, scalars, a sub l's, not all 0, that make this equation true. So far, so good. We haven't done anything earth-shattering. So let's now let m be the largest integer such that a sub m is not equal to 0. In this equation, it might turn out that a sub n is 0, or a sub n minus 1 is 0. So let's just find the biggest of those complex coefficient scalars, and that's what we're calling a sub m, that's non-zero. Now, since we picked this v that was non-zero to begin with, then we know that a1, a2, a to the m, they can't all be 0. So a1, a2 through a sub m cannot all be 0, since that would actually force a sub 0 to equal 0, and we know the n plus 1 vectors are linearly dependent. So we know that that list of coefficients has to contain some non-zero values or scalars. So now we know that m is strictly greater than 0. So this is a strict inequality. And it can be less than or equal to n. So now we have some scalars, a1 through a sub m. Let's build a polynomial out of those scalars. We can use the a sub j's that we now have to write a polynomial. And we'll call that polynomial p of z. So now p of z is going to be a sub 0 plus a1z plus a sub 2z squared. And we can keep doing this. We can even go all the way up to a sub n, z to the n. Let's just do it. We've said we don't know what a sub n is. If it's 0, it's 0. But now we have this polynomial. Here's the plan, because we're not going to get much further in class, but I'll finish it up after class. We now have an nth order polynomial. Knowing what we know about polynomials, we can factor that. Once we have it factored, now we can actually write this in terms of a polynomial of our operators, and we can factor those operators according to the factored form of this nth order polynomial. Then we will essentially show that that has to be 0, and because of that we now know that one of these factors, which let's say we had a z minus lambda, then we have a t minus lambda, we're going to find that that has to be 0 for some one of these lambdas. And if that's the case, then we now have a non-trivial null space that exists, and we can now say that that has to happen at least once for this polynomial to be 0, and because of that we now are guaranteed of having at least one eigenvalue associated with this operator t. So I'll finish this up after class, but that's where we are headed with the rest of the proof. Is we have an nth order polynomial, we'll factor it because of what we can do with polynomials, and then we can apply that factored form to our operator, and now we have these t minus lambda I operators, and one of those is going to have a null space, a non-trivial null space, and boom, now we have one eigenvalue. We'll pick up somewhere close to that in Chapter 5 and maybe finish Chapter 5 the next time we meet.